Roll Tide. Sorry, I wanted to say something a little bit different than, hey everyone, how's it going? Like things like I normally say that in the number of videos that I have made for basically the COVID-19 migration over into the virtual world. And it was just like, I need to say something different. But there you go. So what we're going to be talking about in this video are basically operational amplifiers, or what we like to call as op-amps. It's essentially the basic electronic building block that we see in most electronic components. And the big difference that this element is compared to what we've seen in the majority of circuits 1 or even with circuits 2 are basically passive elements. This is actually an active electronic, nonlinear, although it has linear aspects to it, element, and it acts as basically a voltage-dependent voltage source. So the key word here is actually amplifier. And it gives us the ability to do many, many things other than just simply amplify a signal or invert that polarity. It also is the building block for modern devices that can be used to perform mathematical functions. And we're talking about summation, differentiation, integration, things like that. And you know how this element is actually built is beyond the scope of circuits 1 or circuits 2. But basically this is a semiconductor building block, and we can utilize that to perform all kinds of different functions. And as you guys get into your analog electronics course, much of these building blocks are going to be discussed, and you're going to really get further into the analysis. What we're really going to be talking about for the next couple of videos are essentially the basic nonlinear model non-ideal model that we're going to utilize and actually show how that is used to develop basically what we call the ideal op-amp, in which we use that model to basically do a lot of analysis and actually the building of certain models that allow us to perform some of these functions. So again, the big difference between looking at what we've seen so far as resistors, capacitors, and essentially a inductor is that this is a semiconductor chip, and usually we utilize a 741 integrated circuit for this. And it generally has 8 pins on it. And there's only a few pins on this that we're actually really concerned with. First, the 2 are balanced, and we don't really worry about that. There's nothing connected up at the pin 8. But the pins that we really concern ourselves with are the output, the inversion input, the non-inverted input, and then our power supply, which we actually use VCC anywhere from 5 to 24 volts. Essentially, that's connected not only to basically the positive power input, but also to what we consider as a negative input. And how that actually would work is if we have basically the schematic model of this element right here, the op-amp, then we actually have the inverted input that would go into the negative terminal, and non-inverted input that would go into the positive terminal. On a diagram as far as the power, which we always kind of assume it's going to be power, so we're not really going to be looking at this from here now. But basically, same power supply going to ground, negative to positive, goes into basically pin 7 for V positive, and then negative to positive in this orientation goes into pin 4 for V minus. And so we basically have a range right here of power that's actually going, we could say, from negative VCC to positive VCC, and that just depends upon the element itself and how much power we actually want to put to the chip for allowing for a boost here. Now, when I say boost or basically amplification, basically you cannot amplify the input over essentially VCC. And so once we actually get to say 10, let's just say hypothetically, let's just say 24 volts. If we had a 24 volt supply to it, then there's no amplification that could go over 24 volts, and that's what we basically call saturation mode, in which we can't go over that amplification to that level. Same thing on the negative side of that. We can't go below negative 24 volts either. And so when we analyze these circuits, we're going to start off with looking at the non-ideal op-amp. And we're looking at this basically to segue into why we even consider the quote-unquote ideal op-amp. But just for this video, we're actually going to utilize the non-ideal op-amp to basically give a starting to our foundation of how these elements work. So there's a couple of portions to this. We have two inputs, obviously, V1 and V2, and then we have also our output. Now, whether V1 is the negative input or the positive input, it doesn't really matter because this interior form, this model, doesn't change, in which we have a resistive input that's usually really high, and our resistive output that's relatively low. And then here we have basically what we can see as a dependent source, in which is dependent upon VDD, which is the difference between V1 and V2 with a polarity of negative to positive oriented in such a manner. And so when we look at connections of a circuit that are connected to the output or these two inputs, either one, then we can actually rewrite the schematic in such a way that we can usually solve that with nodal analysis, essentially. And much of the time what we're concerned about is the gain, or what we call the open loop gain between V0 and essentially what we consider as our input, Vs. Now, here, this internal, I want to talk about this a little bit. Usually this gain that we have right here, A is our gain for what we call the open loop gain. And that open loop gain is actually going to basically take VDD and then multiply it by that value. But much of the time when we're concerned with the operational amplifier itself, that open loop gain, it kind of doesn't really worry about what we call, or really correlate necessarily to what we call the closed loop gain, in which we utilize the feedback from basically our output back to our input. And so even though we're going to see this open loop gain right here in the model that we're going to look at for a non-ideal op-amp, we're going to see that the gain that we're actually going to really consider is going to be dependent upon basically the feedback loop that's going to go from the output to the input. And also another thing that I want to say is that, say, for instance, if V1 exists as the positive or non-inverting terminal, what that means is that whatever gain that we get on the output is actually going to give us the same polarity as the input. If this is the negative terminal, then the negative terminal or inverting terminal will actually give a polarity that's opposite on the output itself. A couple other notes to have right here is that VD is equal to V2 minus V1, or in this case, because of the negative positive orientation, we have V2 minus V1. V0 is, in this case, since basically AVD is connected to ground and that's open loop, R0 doesn't really come into play, then that's just equal to AVD. If we rewrite VD and A in terms of our input and the difference in the input, then we get V0 is equal to A times V2 minus V1. So what we're going to do now is go through and take this internal model and we're going to apply it to a schematic and then solve it with nodal analysis. Now, you're going to find that the non-ideal situation is actually going to be a little bit tedious, and we're actually going to see why. And it's tedious from the aspect of we start utilizing pretty big numbers in reference to our open loop gain as well as our internal resistance. So that internal resistance being high is actually going to drive our values. It's just going to make things a little bit, it's not hard, it's just basically, well, tedious. So let's take a look. So this is actually going to be the first, this is the first example that they give within Chapter 5 within the Alexander Sadiku book. And so this one we're actually going to, instead of having basically and an open loop type of circuit, where here we're going to actually have a feedback closed loop going from the output, going through a 20K resistor all the way back to connect up to a 10K resistor to a voltage source, and then that's connected into the into the inverting terminal. The non-inverting terminal is pulled to ground, which we have an output of positive to negative for V naught. Don't erase. Yeah, I had that up here because I left this overnight. So if we redraw this circuit in such a way that we put in the model for the non-ideal op-amp, then in this case we have a connection from basically the 10K ohm resistor. We're going to connect that down to our internal resistance, which is 2 mega ohms. So that's 2 times 10 to the 6. And then we're going to take this terminal, this node, and we're going to connect that to the feedback loop of 20 kilo ohms, and that's going to connect down into V naught, which connects to our output resistance of 50 ohms, and then also A times VD, in which in this case, I didn't write this down, but A itself, that open loop gain was equal to 200,000. And remember, the gain in this case is actually going to be essentially a ratio that we're going to see. And so for here, we want to calculate this closed loop gain here of basically the output voltage to basically our input here. And Vs, it doesn't actually matter what this value is, because what we really concern ourselves with is the gain itself. So the ratio at which, if we put an input voltage here, Vs, what will we actually produce on the output? Now we're going into the negative terminal here, so that means that whatever voltage that we get out here, we should get a negative polarity or an inverted polarity at the other terminal of V naught. So here I went ahead and just applied nodal methods here. And so here we know that this is going to be equal to VDD, or negative VD, negative to positive. So I went ahead and just labeled that as negative VD itself, instead of usually just calling that a, just VX or something like that, because we know that this value right here is actually going to be negative to positive. So in this case, that would be negative VD going to ground here. Now over here, just because V naught exists between this terminal and ground, and we can just allow V naught to exist as that label for that unknown node voltage. And here, that dependent source, we're actually going to drive as basically being this value here. So I drew our currents, I1 going into negative VD, and outputs of I2 and I3. I3 goes through our internal resistance to ground, and then I2 goes to V naught, I4 leaves V naught, and goes to our dependent source with basically that open loop gain. So by going ahead and analyzing our KCL equations and then expanding those, at node negative VD, I1's equal to I2 plus I3. So Vs minus our unknown node, which in this case was negative VD, over basically 10K, and that's equal to negative VD minus V out over 20K, and then plus negative VD over 2 times 10 to the 6, or 2 mega ohms. And that's going to be really small values within here. So I'm just going to go ahead and just multiply through times 2 times 10 to the 6 and see if I can get and rearrange the equation in such a way that we get some better values on top. So here we get, when we combine like variables, we get 200 times Vs is equal to negative 301 Vd minus 100 V naught. So let's take a look though at node V naught. And you should already be seeing that this, working with mega ohms in this case when we just got K over on the other side, should be causing you to question this just a little bit. Like, you're saying non-ideal. Maybe wondering what ideal is in terms of an op-amp operation. We're getting there though. So let's look at node V naught. So here I2 is equal to I4. I go ahead and expand that, so negative VD minus V naught over 20K, just like we had up here. That's equal to V naught minus AVD divided by 50. Well, the problem is if we just leave VD in here, then we actually are going to have more variables in the equation that we actually want to deal with. Same thing up here. So I'm going to go ahead and expand, just basically, sorry, I'm not there yet. Sorry. Just went ahead and rewrote this in terms of V naught minus 200,000, that's our open loop gain. Excuse me about the VD thing. We're getting there in just a sec. So 200,000, and that's our open loop gain times VD divided by 50. I go ahead and rewrite this equation, multiply through just to make the equation more in terms of whole numbers. So we get negative VD minus V naught is equal to 400 times V naught minus 200,000 times VD. In this case, we get minus 401 times V naught, and that's equal to negative 199,999 VD. So if I consider this as 1 and this is 2, I want to get rid of this VD down here. So what I'm going to do is rewrite this equation in such a way that I could substitute VD into this equation down here, and maybe by substituting that equation, then I'm going to have VS and V naught. And if I have VS and V naught all in one equation, then I can rewrite that ratio and actually find that closed loop gain that we actually see. So let's actually rewrite number 1 in terms of VD, and we're going to substitute that down into number 2. All right. So if I rearrange number 1, that's going to basically, so we can isolate VD, we get 200 VS plus 100 V naught. That's equal to negative 0.667 VS minus 0.332 V naught, and that's equal to VD. So if I take VD now and substitute that back into our equation, this just looks messy. It looks like, oh God, these are large numbers here. Negative 401 V naught is equal to negative 199,999 times, in parentheses, minus 0.667 VS minus 0.332 times V naught. Minus 401 V naught is equal to 133,399.3 times VS. That's equal to 66,400 times V naught. Now we basically have the equation all in terms of V naught and VS, and by that notion we could actually find the ratio of V naught to VS. And if we do that and combine like variables, and then isolate the variables V naught divided by VS, we find that that ratio comes out to be equal to essentially negative 2, or negative 1.997. And so that means that if we had 10 volts on the input, the output is actually going to have a gain of negative 2, or come out to be basically to negative 20 volts. So it inverts that polarity because we connected that to the negative terminal. So in the next video, we're going to do another problem that's going to basically exemplify why we don't really, in our initial discussions of operational amplifiers, actually really consider this non-ideal operational amplifier. You should see that lots of these numbers that we had in this example were really big due to not only the internal resistance of basically our two inputs, but also basically that open loop gain on the output. And so we may be able to go through and determine a different way of an equivalent model that would simplify our analysis greatly. And so for the next problem that we're going to do, we're actually going to do just like the book does. The book actually goes through and gives an example where we show how to use the non-ideal op-amp. Then they actually give you a practice problem, 5.1, practice problem 5.1, in which they go through and tell you to solve it with this method. And then they do a correlation with that problem utilizing an ideal operational amplifier, basically to bridge that gap. And so that's what we're going to do in the next video. This one is basically just to give an introduction and also kind of get you guys to see that some of the values in here are quite large, which makes like this almost like paradigm where we got these large values and very, very small values, and how maybe we can mitigate that. So Next video is coming up. We're going to do the correlation between the two models, and then we're going to start discussing about some applications and uses, just like I said over there in terms of summation amplifiers, maybe differentiation or difference amplifiers. But we're going to get there and actually start showing how to utilize these to perform very, very specific functions. You've already seen one function today, and that's specifically a gain. And that's really, really cool stuff. That actually opens up a whole new world for, I mean, some of the reasons why I've told you guys why I'm even involved with electrical engineering is because of the musical aspect of it. So amplification, it's one step right here into a much larger world. So see you then.